that the movie is Legend of Halpern-Leistner. So they tell us about its patches from the end of the stability manifold.
Okay, so all right, thank you for the invitation. So I had originally conceived of this as a, well, I previously only talked about this in a sort of colloquium format that really just stays at the very high level. And so the organizers very graciously invited me to give 2 hours of lecture, so I figured I can go into more details on these compactifications of stability manifolds. And a dear friend told me that that sounded excruciating. So I should at least give a little bit, start with a little bit of an overview of the motivation. And it's going to be sort of a story about what led me here, and then discussion of some work in progress, trying to make sense of it all. So, the motivation is this noncommutative minimal model program. And so this was my attempt to formulate or give a more precise formulation of various conjectures that have been swirling around in neurosymmetry by Kontsevich and other people, that you should have canonical semiorthogonal decompositions of sort of arbitrary variety, arbitrary smooth, the derived category of arbitrary smooth projective varieties. So I was thinking about this a little bit. So the goal of this project was to formulate a slightly more precise conjecture that explains canonical SODs. Like, where should they actually come from concretely? And so the basic idea was that, so the usual MMP, you can think of it as, this is not really the way that birational geometers think of it, but it's the way that mathematical physicists think of it. So the usual MMP is basically studying canonical paths in H11 of a variety. So you're sort of varying the Kaehler class, and as you do that, it stops being Kaehler on one model, but then becomes Kaehler on a birational model, and you end up exploring the whole movable cone. So the analog requires the noncommutative analog should basically be discussing some canonical paths in the noncommutative analog of the Kaehler moduli space, which is this complexified Kaehler moduli space, which still doesn't have a completely rigorous definition, but there's a larger space called the space of Bridgeland stability conditions. And this is meant to be, this is analogous the Kaehler structures. So this was my line of thinking on this, and actually the paths are going to be live in the stability manifold quotient by the natural action of the additive group of complex numbers. So so let me just explain. So I should explain what this is. So I can't. So basically, a stability condition consists of the following data. So a stability condition on a triangulated category So I guess you have a slicing. So a collection. Collections, P of phi of objects, so-called semi-stable objects for every phase phi. And you also have a central charge. So I should say, typically, and through this talk, what you'll fix is an analog, a categorical analog of a Chern character map. So it'll just be we'll fix once and for all homomorphism from K naught of the category C to some, this is a lattice. Finite rank free unit group. So the central charge is a homomorphism from lambda to C, such that I guess so Z of P of phi should lie inside of the ray, and by e to the phi comma phi. And there should also be, so these are the conditions that should hold, and there should also be existence of Harder Simon filtrations. Which is a filtration, a finite filtration of the object such that GUR I is semi-stable, it lies in this category P of phi, semi-stable phase phi. And then there's also one other condition, which is sort of added a little bit later, which is the support property. Which basically says that it says that the size of the central charge of semi-stable objects can't get too small relative to the norm of I should say the norm of their Chern character. Well, I'll just say, so whenever I apply a function like Z to an object E, I'm implicitly applying it to the image under this Chern character map. So this should be bounded below. And so Bridgeland's theorem is basically the starting point of this subject, and that basically the theorem is that these have a metric topology. And sometimes you put the lambda there just to remind people that you fix the Chern character. This has a metric topology. Such that the forgetful map that just keeps the central charge is a local homeomorphism. So part of the reason why I recall the definition, just assuming that maybe not everybody has played with it that much or seen it, but also because over the course of this talk, we're going to be revisiting this definition and reformulating it in slightly different ways. So I figured here we're going to get a little bit in the weeds with this actual concept here over the course of the talk. So I might as well put it up there so that people can get it back in their mind. So, but this theorem here is important because it makes a connection between the stability space, which is now via this theorem, it's a complex manifold, and the space here, which is, you can think about in practice. So what I mean by that is for in the practice of algebraic geometers, C is dB of x, and this is really a twisted is the twisted Chern character now. And we'll usually assume that the Chern character is surjective. So I'll just sort of define this to be the image of this twisted Chern character. It's twisted so that it's a map of Hodge structures from topological K theory to homological. Okay, so this Bridgeland's theorem gives a connection, a relationship between well, what we're looking for, which is paths in the stability manifold, which I mentioned. This should be the noncommutative MMP, is paths in the stability manifold, and paths in Hom from lambda to C. So it basically paths in the stability manifold are basically the same thing as, well, you have to start with some stability condition, but then after that, the path is just completely determined because of Bridgeland's theorem by what it does in the dual of the lattice lambda. So yeah, and so this sort of suggests an answer. So what are the canonical paths instead of x on C? So the answer is just, well, there's sort of an ansatz. And this is basically the non-commutative MMP, as I formulated it, is that the solutions of the quantum differential equation, should I say truncated, lift two paths in stab of x mod C, and that these paths they should reveal somehow SODs in X. And so I have to explain that's, you know, to the extent that my paper on the NMMP had results in it, it was an explanation of what this mechanism is, that you would take a path in the stability manifold and actually extract from that a semiorthogonal decomposition. But this perspective was inspired by work of Libmill and Gabe Kerr and Matt Ballard and Colin Deemer, I think. So basically, you know, it basically comes from mirror symmetry. It's an attempt to reformulate in purely categorical terms this idea of considering Fano mirror symmetry, non-Falabian mirror symmetry. So rather than, I don't want to go into the whole thing because I'm trying to, but I'll just explain the most beautiful example. So the papers that I mentioned, we're doing more complicated toric examples and saying, how do you get semiorthogonal decompositions of toric varieties by studying their Landau-Ginzburg mirrors? But the example that I understand well is the example of T1. It's really the best variety that there is. And so, right, so in this case, the idea is that the mirror so the derived category should be the Foucault category of C star with this potential, I've chosen maybe unusual parameters just because it made my formulas work. So W tau of x equals plus e to the 2 tau divided by 4x. Okay, and tau is a complex number. Oh, I said, oh yeah, I should say that there's something that's like a little, so in Maxime's talks, you're always working over this non-Archimedean field. In my situation, in my context, the stability manifold is just like an actual complex manifold. And so I needed a different way of avoiding convergence issues. So rather than working over non-Archimedean field, I just suggest that we truncate the quantum differential equation and only include the terms that count basically kx positive, kx negative curves. So those are the only ones that sort of contribute as the q parameter goes to infinity in some sense. Those are the only ones that contribute. And so the argument is, well, just only use those curves and count that differential equation. It's not part of a Frobenius manifold or anything like that, but it should define a path. And maybe by the end of this discussion, it'll seem plausible that that's like a reasonable thing to do. But at least it's something that you can actually imagine. It's an honest path in an honest complex vector space that you can then lift to the stability manifold. Anywho, in this example, so you have this parameter tau, and the critical points, the critical values, I think, are plus or minus e to the tau. And so as the real part of tau gets very, very large, basically the two critical values move farther and farther away from each other. And there's for geometric reasons, when you have this phenomenon, the critical values move far apart. Eventually you get a semiorthogonal decomposition in the Fukaya-Zio category, is my understanding. So that's the kind of analysis that Lugmill and his collaborators were doing, where they were considering the Landau-Ginzburg mirrors and looking at asymptotics of, I think they were looking at critical points, but critical values is similar. And then trying to break the category by hand into different pieces. And so what I'd like to explain is that you don't actually have to do it by hand. You don't have to guess what the objects are, that it sort of comes from the stability condition. So what is the stability manifold in this case? So, I mean, the stability manifold is a two-dimensional complex manifold, but when you quotient out by the action of C, which just basically multiplies the central charge by, e to the alpha, and shifts the phase of semi-stable objects appropriately. So if you quotient out by that action, that's a one-dimensional complex manifold. And actually, it's isomorphic to just C, but in a very interesting way. So the theorem, which I guess was sort of expected from this mirror symmetry thing, but you can actually in this case of P1, you can prove very directly, is basically for tau in R plus, I guess the interval I pi times the interval from k to k plus 1. So you have these strips in the complex plane. Let's say this is pi k. I'll focus. So the strip here, there exists a unique stability condition such that with O of k and O of k plus 1 stable, and the central charge is sort of what you expect, Z of E. Oh, sorry. So Z tau, the central charge of the stability condition of E, is the usual formula. So there's some you get some sort of SYZ mirror symmetry that takes you from objects in this derived category to curves inside of C star. And this is the integral of e to the minus w tau of x dx over x. So there's sort of a unique in this for tau in this strip. There's a unique stability condition with these properties up to, I guess, shift by 2, homological shift. You can't tell. Well, I think I have a backward 1/2, and I don't know wrong with it. Anywho, so the stability manifold sort of looks like this. And in each of these strips, so let me draw. So you have these regions in the stability manifold, like this. And in here, so the whole region where so the whole region where O of k is stable, is O of k is stable in here and in here, and actually everywhere out here too. So there's a picture where you have these kind of lobes, and in this region, the stability condition is glued. So it basically the only stable objects in this lobe, the only stable objects up to shift are O of k and O of k plus 1. Outside of these lobes, it's basically just slope stability. So there are many stable objects. I mean, many more stable objects. All the line bundles are stable, for instance. But in each of these lobes, basically all that goes away, and you just have these 2 stable objects. And the stability condition there can be constructed from via a procedure due to I guess McCree in this case, rather than Collins and Polishchuk, basically from the semiorthogonal decomposition, dB of Q1 is O of k and O of k plus 1. It can be just constructed from saying what is the central charge of those 2 objects. And so when you look at, so now the claim is that when you look at the solutions of the QDE, so this is now a solution of the QDE. For the solutions of QDE lift to paths like this. So as shown, so it's basically log of t plus some constant. This is tau. So the parameter, the parameter in the stability manifold is just when you take the solution of the quantum differential equation, lift to the stability manifold, this is the path that you get. And so the path is just going right, exactly to the right. And in fact, let me zoom in a little bit more. So this is again, this is I by k. And along this, basically, if you start, I guess I shift up from this line by I pi theta for some number theta, and then I go straight to the right. If I look at the difference, eventually you enter a region where the stable objects are OK and OK plus 1. And if I take the difference, log z of OK plus 1 minus log z of OK, it just looks like So in this region, it looks like e to the I pi theta times t. These paths, which I'm claiming to you are the lifts of solutions of the QDE, the asymptotics has this form. And likewise in this region, in the region below, if you start with theta being negative, this is now you're in a strip. This is now the strip where OK minus 1 and OK are the stable objects. If you start with a little bit below this line with imaginary part pi k. And in this region, log z of OK minus log z of OK minus 1 is e to the is minus e to the I pi theta times t. Okay, so what happens here is if you started to say, let's consider some objects that are stable as you move along this path. So I can start somewhere in the stability manifold. I lift the solution to QD and I say, what are the stable objects? You would find that eventually you're basically the only objects that stay stable forever are OK and OK plus 1. And so not all objects have a log of the central charge being well defined, but stable ones do, because you can define the imaginary part to be correspond to the phase. The imaginary part is just pi times the phase of the stable object. So this log z of these objects is well defined, and their asymptotics look like this. So basically, you know, if theta is positive, the imaginary part of this thing goes to infinity. As t goes to infinity. And so you have two objects, and they're semi-stable in many, many different stability conditions, but their phases the phase difference between them is going to infinity. And if you think about it, oh, I forgot to mention this, but if you think about it, in the definition of a stability condition, there are no harms, not R harms, just harms. There are no harms from an object with higher phase to an object with lower phase. But because these objects, the same objects, are actually sort of semi-stable with larger and larger phase separations, there actually are no R harms in one direction. So you can deduce, if you have these objects that stay stable along this path, and you know that the log of the central charge, the imaginary part is getting larger and larger and larger, then you actually know that there can be no R harms in one direction to the other. And so the semiorthogonality of these two objects basically comes for free from the fact that they remain stable as you move in this direction. It's a consequence of the fact that they remain stable as you move in this direction in the stability manifold. And so the first step of the project was to kind of generalize or to sort of formulate a general mechanism. So and this was the first version of this is called quasi-convergent paths. And roughly speaking, it's basically I'm not going to talk today about quasi-convergent paths. I'm going to talk about the next thing, but the quasi-convergent paths thing is this nice little self-contained paper, and it explains that you have lots of objects. So more precisely, so C will sort of be generated by objects that are limit semi-stable. So it's a path sigma t in stab of the category C. limit semi-stable. Oh, and I should say that there's a reason why studying the central charges makes sense. You know, from the mirror symmetry point of view, it's this kind of, you know, instead of studying the critical values and the critical points, you can use the sort of method of steepest descent and relate that to the actual values of the central charge. They should have the same asymptotics, roughly speaking. So you could geometrically, if you have the mirror, you could study what happens to the critical values of the Landau-Ginzburg potential. But if you don't have a mirror, but all you had is a stability condition and a path in the homology ring, you could still ask what happens to the asymptotics of the central charges of semi-stable objects. So the quasi-convergence is an attempt to basically lift this example to a general homological fact. So limit semi-stable means basically that the largest phase, the difference between the largest phase and the smallest phase goes to 0 as t goes to infinity. So they're not exactly semi-stable, but their phase is concentrated in a smaller and smaller region. And then the other thing is that I want so this is like one thing, that you have enough of these limit semi-stable objects, and then if I take the difference and I normalize it, so log z of e minus log z t of f divided by the norm, the same, converges in C. So if I look at just the difference for limit semi-stable objects. And it turns out that these two conditions, that you have enough of these limit semi, you can generate it by limit semi-stable objects, and the difference in the log central charge of limit semi-stables sort of converges after normalizing, is actually enough to construct semiorthogonal decompositions of the category where the factors are generated by limit semi-stable objects. You basically group the limit semi-stable objects by the asymptotics of their log central charge, and you use this observation that I mentioned before to say that, okay, well, if the imaginary part of the log central charge is flying away from each other, then they actually have to be semiorthogonal decompositions. And there is a situation where the imaginary parts are not flying apart, so but only the real parts of the log central charge is flying apart. So in other words, when the central charge of one object is going to 0 relative to the central charge of the other object, and that fits into this framework as well. But there's a more full picture that I guess I am going to explain now. So yeah, so rather than go into more details on these quasi-convergent paths and the noncommutative MMP, what I really wanted to do is, if you stare at this picture and you're studying these solutions of the quantum differential equation, sort of an obvious thing presents itself, which is that these paths should be converging to some point at infinity. So namely, I should just attach a real line here. Let's say, call this, and the real line at infinity, this real line at infinity being existing a manifold with boundary, and these paths are now converging in this partial compactification. And so the question that I wanted to answer was, what is this partial compactification? Like, what is it? And that's what I'm going to tell you about, basically. Like, what is this partial compactification? And I've been doing a deep dive on this question, and it's led to some interesting things that come out of it. So, you know, one thing that this partial compactification tells you is it basically gives you, you know, local coordinates in a neighborhood of infinity on the stability manifold. And so in principle, these are kind of like the flat A model coordinates in mirror symmetry, but you can formulate them entirely just intrinsically on the stability manifold. So this is still conjectural. So there's a piece of the story that's still conjectural. At the moment, I've constructed this space, and I can tell you what the objects are and how to topologize it. That's what I'm going to do. And I'm going to very clearly formulate the conjecture that it's a manifold with corners. And that's the so-called space of augmented stability conditions. And one of the nice things, if this conjecture is true, is it would give you these local coordinates in the neighborhood of infinity in the stability manifold, and that would tell us a lot more about sort of the structure of the stability manifold at infinity. But another very unexpected thing that came out of this was that if this manifold with corners conjecture is true, it actually implies simpler conjectures, much simpler conjectures that actually also imply the existence of moduli spaces for semi-stable objects. And so you get something like as I was saying, like originally, I wasn't sure if this manifold with corners conjecture was difficult or not, but it actually has this really cool implication in the moduli theory of objects in DG categories, which convinced me that it's actually a kind of a subtle question. Oh, so I'll try to explain this. I'll explain all of that in the course of the remaining 3/4 of my time. So
what combine when the differential equation?
yeah, I interpret the quantum differential equation. I only restrict it to the algebraic homology, and I interpret it as a there's no parameters. It's just I interpret it as an honest differential equation valued in the algebraic homology, the image of this Chern character map. It's an ODE in a single complex parameter. Yeah, it's the anticanonical line. It's C1 of X. It's like C1 of X. And then I guess it's like yeah, it's like and then but then I guess you can also allow I add a parameter there. So there's actually sort of a family of differential equations. Yeah, so there's a family of differential equations, but they're parameterized by this parameter psi. Yeah. I'm solving always in the direction of C1 of X, but from different starting points in the Frobenius manifold. Yeah, that's what I'm doing. Yeah, except that I truncate to avoid convergence issues. Yeah. In the P1, in the Fano case, you don't really need a truncate. It only comes up when you have when you have when you have yeah, so okay. Right. So before I tell you about all this stuff, what is this boundary and what does it have to do with other interesting conjectures about stability conditions? So I want to first have a little bit of fun. So I want to revisit what is the stability condition. So, right. So this thing above, this discussion that we had, I think should make it pretty clear that in this story that I'm about to tell, it's not the central charge that plays the leading role, it's the log of the central charge. And now the issue with the log of the central charge is that it's only kind of partially defined function. It's only defined on semi-stable objects, and implicitly you can define it on objects whose, as long as it doesn't have to be semi-stable, but as long as the fade width is very narrow, you can also define log of the central charge. But I'm going to talk about a different way to think about stability conditions. So, namely, for any stability condition on C, you can associate to it this finite measure. I'll call it dm Oh yeah, for any so for any object, non-zero object, you can say, okay, dm, I guess sigma comma e is the sum of these delta functions where the gi are the graded pieces of the Harden-Sinhan filtration of E. Okay, well, that's not, I mean, yeah, it's just a different way of encoding the data of the z's of the thing. But then this has a sort of, I don't know, this perspective is interesting, was interesting to me because the space of measures itself has a weak topology, and you can, it's basically obvious that the stability manifold embeds in the space of functions from C minus 0 to the space of finite measures with its weak topology. And so you get this embedding of the stability manifold in some enormous space, and you can try to compactify by taking the closure in there. So there's like already from this perspective, it's suggesting certain ways of enlarging the space of stability conditions. But I also want to say before I do that, I want to say this gives you some functions. So the ones that have been studied before, especially in the context of this dynamical systems and categories and that sort of thing, categorical dynamical systems. So you can say the integral of e to the t theta, sigma e theta. So it's just a fancy way of writing, a sum of the norm of the central charge times e to the t like that. But this function has been studied before. There's another function which is sort of interesting, which is what I call the smooth phase. So I can say phi t. So this is defined to be the following way. It's so when t is 0, this is the average phase of the GIs with respect to this measure. So basically take the average phase of a semi-stable object with respect to this mass measure. And this is if t equals 0. And otherwise, if t is non-zero, you can do like this. And this is it's sort of a cool object. So basically, this allows you to say what is the phase of any object. It gives an answer. It's a continuous function on if you fix an E, it's a continuous function on the stability manifold. And it says, okay, this is like the best approximation of a phase. Of course, if the thing is semi-stable, so this mass measure is a delta function, then it just agrees with in t equals 0, it just gives you the phase again. But in general, it's analytic in T. And it kind of looks like this. So it's strictly monotone increasing. I mean, when E is semi-stable, it's constant in T, and it's just always equal to the phase. But when E is not semi-stable, it's analytic in T, and it's strictly monotone increasing, and it goes from, so this is like the phi naught of E. This is average phase. I'll just call this phi of E from now on. This is average phase. And it converges to, as t goes to plus infinity, it goes to what's called phi plus of E, the phase of the largest Halpern-Leistner factor. And out here, it converges to phi minus of E, so the phase of the smallest. So this is like some kind of smooth interpolation between saying what is the smallest phase of a Halpern-Leistner factor and what is the largest. And the middle one, the phi zero, will have a special role. And so, yeah. So for instance, you can detect semi-stability. So Jensen's inequality for this finite measure implies that if I take m of e to the t phi of e, this is always less than or equal to mt of e, with equality if and only if e is semi-stable. That's the first hint that actually these functions are actually enough to detect semi-stability, not just, they record the central charge, but they're also enough to detect semi-stability. And so the main function that we're going to be discussing is a combination of these in a reasonable way. So the main character here is what I call L sigma of E. L stands for log, log of the central charge. So this is instead is log of the mass plus I pi. You can put a t up here if you like. So I pi times phi t. So this is now a complex number that's defined for any non-zero object in the category, because the mass is just some positive number in that case. And it's a continuous extension. If you consider the closed subset of the stability manifold where E is semi-stable, this is now a continuous extension to the whole stability manifold of the log central charge function. And it makes our lives much easier to just be able to say, okay, this is like the log, we treat this thing like the log of the central charge. But I mentioned before that if you just remember the mass measures, then if you just remember the mass measures, then you remember the stability condition, because you can just read off from the mass measure if the objects are semi-stable. And so you can think of the data of a stability condition as a bunch of finite measures for every object that satisfy axioms that are basically just translated from Bridgeland's axioms. But you can think of the basic data as these mass measures, but it turns out you can also, you can embed so into the space of functions. To the c minus 0. So in other words, functions from c minus 0 to the complex numbers. And basically that you take sigma to the function that takes e to L sigma v. And it's not a difficult, but it's a slightly non-trivial lemma that this is actually an embedding. T is equal to 0, yeah. Well, sorry, when I drop the t, it's all of my functions have these t deformations, but when t equals 0, I'll just drop the t from the notation. And so there's this like little lemma. So basically, right, so you can recover, I'll explain why this is an embedding, but you can recover the mass function from this. This is just the norm of E, the L of E. Okay, so if you know these kind of log central charge of every object, you can recover its mass. And then the mass function for a stability condition satisfies the triangle inequality. So for every exact triangle, E goes to F, goes to G, you have an inequality like this. And there's a little lemma that says that F is a stable object. F is stable if and only if this is strict. Whenever E and G are non-zero. So in other words, you have the trivial extension where this will just automatically, if E or G is zero, then it's just trivially an equality. But F being a stable object is the same thing as saying that any other time this triangle inequality is strict. And so if you know the mass function, you can recover what are the stable objects. And then I mentioned that for stable objects, this L sigma is the log of the central charge. So then for stable objects, once you know the stable objects, then the phase of that stable object is just this, 1/pi times the imaginary part of L of E. So then you recover the stability condition because you know what the stable objects are, and you know what the phases of the stable objects are. Anyway, so it's just a sort of cute thing, but it suggests something interesting. So basically, a stability condition is now in this formulation an assignment of every object to a point in the complex line. And so, okay, as you move in the stability manifold, this collection of points, it's really like an infinite collection of points because you get a point in C for every object in your category. And now as it's moving around, like the points are sort of moving around and going off to infinity in different ways. And so a very natural perspective from this as well, if you could sort of compactify the configuration space of C, then that will lead to a compactification. So of the space of stability conditions. So the idea is, so if you have a bunch of objects, En in C, then like L sigma will take this E1 through En to some point in the configuration space, but really it's just in C to the N. But, and I will say that, so for reasons that I maybe haven't made clear, but you can just take on faith. So L sigma, it'll be more convenient for us to work with stab mod C. So L sigma is not, if I take a complex number and I take L sigma of E, this is actually equal to L sigma of E plus Z. So that's what happens to the log central charge if you act on the stability condition by a non-zero complex number. And so if I want to say what is the stability, if I want to embed the stability manifold mod C, then the L sigmas are not well defined. So I can take L of E, which I define to be L sigma of E minus L sigma of F. Somehow like the difference between the log sigma, the log central charge is well defined on stab mod C star, stab mod GA rather. And so the idea is that you get a bunch of, so for every collection of objects, you get a bunch of points. And I'm going to now see pushing by the diagonal action. Right. And so, so actually really what the L sigma is defining is not, for every collection of points, what I get is a map from stab of C to this quotient. And so the idea is, well, if we want to compactify so if I want to introduce points at infinity where the log central charges of different objects are flying off to infinity in different directions, what I'd really like to do is to compactify this space of C to the n mod the diagonal action. So that's what basically what I will be doing. So I'm going to define these objects which are at infinity, called augmented stability conditions, and it comes from a particular geometric compactification of C to the n mod C. So I think I'm sort of at a little bit of a funny break point here, but let me just I'll give you a flavor of what's going to go on here. So so C to the n mod C I can think of as, so this is actually the space of lines. So it's the space of curves, genus zero curves. Well, actually, let me just do it this way. So I'll define the key this new geometric object. So definition: a multi-scaled line is a tuple. So it's a so sigma is with point at a marked point at infinity is a nodal genus zero curve. And then there's what's a symbol like this is a total preorder. On the dual graph. And then there's also a collection, omega v. This is so the dual graph, its vertices correspond to the components of the curve sigma. And so omega v is going to be an element, it's going to be a differential form on sigma v that has a pole. So let me just draw a picture here. So there's a marked point, P infinity, and that connects to one component. And now you have a genus zero curve. So the rest going down here is given by a tree. And part of the data is a total preorder, which basically is like a level function. So I'm saying I'm dividing the vertices into different levels, higher to lower, et cetera. And then, so every vertex, part of one of the conditions is that every vertex should have a unique ascending has a unique ascending edge. And the omegas for every vertex corresponds to a component of the curve. And I want a differential form in there with a pole of order 2 at the point connected to the component above. And no other zeros or poles. Right, exactly. Yeah. It's essentially a combinatorial gadget. Yeah. What?
This one was like busy.
Yes, exactly. Right. This form. So basically, each of these components is a P1, and there's a point that's at the top that connects to the graph going up, and then there are a couple of points below that maybe connect to the ones below. And the point is that this thing, at least if I punch out this, oops. if I remove this point, this thing becomes isomorphic to C with its differential dz. And that isomorphism is canonical up to translation. And that's exactly what's going on. Remember the L sigmas, if I consider them from stab mod C, the L sigma of an object is only defined up to translation. So this kind of, this idea of a curve with differential with poles of this kind is exactly capturing that ambiguity that I want to say when I want to quotient the stability manifold as C. So, right. Oh, and yeah. There's a mild condition. The internal vertices should have valence 3 or more. So this is not actually one limit here. So inside it's stable, but of course the terminal vertices, you know, they'll just have valence. So the minimal vertices will have valence 1, but all the other vertices should have valence 3 or more. So these are the objects, and the idea is that the moduli space of such things will be a compactification of the simplest version is just where there's just where the dual graph is this. And if I consider the moduli space of multi-scaled lines along with additional mark points on minimal vertices, then generically there's just a single component, a mark point infinity, and it just looks like a collection of points in C up to translation. The generic point is just C to the n mod C. But now you allow it to degenerate in this sort of way. So I'll stop here because I'm out of time, but this will be the geometric basis for this compactification of the stability manifold that I'll discuss in my next lecture. Thanks.